SwayamPrabha. Digital India. Educated India.
Dear learners, Advanced Thermodynamics, we are in module 2 exergy. Second lecture, that is analysis, that is part, and in this lecture first one is theorem and second law of thermodynamics. In fact, somebody seen the first, then next segment is that is heat and entropy. Lecture we most reversible processes, and the third segment of this entropy for states, that means normal state, we assume final states are in, and if circumstances, if that, how do you calculate the segment of this lecture of increase in the, and we can say law of entropy. The Clausius theory for a scale in the previous, it says is that particular considered that entire cycle is in terms of segments, or the closed path of the reverse is replaced to it closed but zigzag system of isothermal and each one Carnot cycles, many number of Carnot cycles for this closed cycle. What we found is that of the Q by T. So, this was the stated as a theorem for reversible process. What it is theorem states cyclic integral of the parameter is always 0 process. Another form of this, so here, but particular theorem is to Clausius theorem. Okay. In fact, this is the basis of to consider the and calculates it. So, to do particular figure which we in I, and the x certain quantity of work dq heat is receiving, and it amount, but in that in doing so only for this engine we can maybe we can say that 2 temperature reservoir source irreversible engine, that x dq amount of T, and this engine which says that invisible temperature T dash is where they reject the heat, dW amount of work. You can see that when it heat, it is nothing but heat rejected by a reverse. Essentially, the entire look at the reverse are dq1 amount of force at T1, dq amount of irreversible engine, this and produces dW amount. So, in fact, reversible and irreversible, this entire things. So, you can say this is the system. Combined system consists of engine as well as the, and if you look at and another important emphasize that for the, that is this. Now, this d when T dash is equal to T, when T are equal to T, dq, this is nothing but from the second law. This is the conclusion make. When you talk about this reversible engine and irreversible, it seems that systems receives d and it produces amount of work possible because it of thermodynamics, or which means that heat rejection, that means this interacting only, this is possible only that means if the Kelvin state. So, for that, so this must give dW cycle of the engine dW is less than 0, and this implies to have dq1 engine is or say the net work cannot be positive, exchanges heat where. So, the cyclic heat, that is positives, hence must generate heat out of the system. So, that means another reservoir, this another reservoir temperature T dash. When positive, when this T are equal to T dq, and for this T dash and equal. So, represented in a mathematical right, first thing we say based on the Kelvin Planck right, dW, integration of dW for the n0. So, this one is also, this reversible engine is in this temperature source at temperature Q1 amount of heat, and again we will talk the temperatures reversible engine interacts and T1, right, of heat to temperature 1 is equal to minus, and in fact this minus d, this dq reversible engine, it is negative, absorbed by this irreversible, now replaced with negative side. Irreversible engine if you goes off as a this particular here for with respect to E. Now from this simplify these equations, what is the fact that irreversible engine I dq equal to 1 by dq for R, because it is a resistance. So, it is taken, you can see here this T1 here, and finally particular expressions in terms of this, that is cycle is actually integral of for an irreversible engine is T1 integral of reversible engines. What we can, here we can say that than 0 because it is always, and dq1 is less, we have concluded from the Kelvin. This means that you would be less than 0, what we call as Clausius. Now there are we have equality sign for, now we have proved this inequality situation. So for dq by t is 0, full cycle the integral q by t is less than 0. Together we can frame statement of second law as a Clausius inequality. So it says the cyclic or the integral t is always 0. Next segment we have to with respect to irreversible to elaborate more C and entropy, change in the entropy of heat. We are now in which from an initial state I during an E to the final state F to the initial state, that to analyze this relation in irreversible process, this temperature entropy, in this temperature and entropy state I first, and we want to go that is to the final state F. Our analysis is focused on, we assume that there is some kind which is denoted and it is proceeding in this direction. Now by return reversible path, and this is an trying to say that to entropy for this reverse. So remember one thing, path function but functions. So it depends, entropy is independent of, we must know that difference in the initial states. That is one point. Say that during this reversible, what is the that is going into reversible, and if it is not a reversible. So entropy separately. So let us this entropy function integral of ds. This integral of ds evaluated for the cycle, it goes in this way and in this path, two paths. The entropy for this and entropy reversible path. So this to f. So integral of s plus from f to I integral for the reversible path. Combining this together, this is what for you, and with respect from this equation replace this q by t. So it's but this cyclic integral, this irreversible path is always, and in fact when you want and this so on subtraction, that ds sits here, second it is also here, there is a negative sign here for this equation to 0, because in this case it is greater than 0, both subtract, this will take be greater than 0. Interestingly, if you look at and try what by definition of is ds in reversible process from I the same reversible process, from reversible term will get cancelled, term will remain. When you only process, we end up in that ds process when it goes from always greater than d from I to f, that means greater than the cyclic integral. For the very small change we can remove this integral, so we can represent differential for ds of irreversible is greater than dq by irreversible. In other words, in a general any process write this by putting an signs where it says always greater than or equal by t. Now having have our consequences from our so let us that what happens, the possible sequences heat, we have the processes that can heat, process can be adiabatic, the process can be and again for this matrix we may have or E, okay, and Sabin say it's an isentropic, entropy does not change, non-isentropic process, okay. And these things irreversible or irreversible. This is the best analysis. So, evaluate mathematically consequences we are going to think. We say by definition we say ds heat transfer dqr by, and this process your ds equal to 0. Qr stands for that happens in a reverse, and as you always we as reversible addition dqr is, so this is the truth. There are other possibilities. Finally, we can that only this is possible, which means reversible adiabatic path means. Now, let us evaluate first by definition we say d, so this means d less than or equal to, that means to say by t is less than, which means this is inequality. But this equality if the process is, so what of isentropic process does not talk about, okay. From this analysis that if 0, which means or d process is irreversible, expressions two possibilities 0 or dq less than, see 1 by 1. So, process is reversible entropic, so means 0 and ds is equal to dq is equal to 0, and means this process has, because now process is isentropic and adiabatic. Process is isentropic, isentropic means your adiabatic means is d, then it has to be a which means equal to 0. In other words, we can write the isentropic adiabatic be irreversible, isentropic adiabatic irreversible. Simple sense normally refer the same concentropic process reversible adiabatic process. Now, let us move towards situations. So, the case isentropic, isentropic means your isentropic means your ds, but it is your dq is this will come equality. So, the process is irreversible, but it is of course a non, but dq, so which means in an irreversible process heat goes out of the system. So, dq is always less than 0. Category process is irreversible. So, by irreversible we are looking into, and by adiabatic I mean q is equal to 0. Things equation there, that if you see 0 process is irreversible, we can say E must be always 0, that means temperature is. So, in a sense entropic process increases. Summary that has come out irreversible process and entropy. Now, till this far we have evaluated the initial state, P, heat. We are mainly focused equilibrium state, that means always initial state and final equilibrium state, thermodynamic, that means it is say thermodynamic equilibrium, force are 0, no chemicals are satisfied. What happens then if it is states, then so there are some in the nature where equilibrium states it is not states. The calculation of entropy with the irreversible process, following observations, that all only entropy changes. In fact, for all analysis reversible processes we have seen not change at all, but only observers both in of the systems and initial and final states of the system, which are reversible process. If your initial and final that then can say that actual process is irreversible, this actual process is one. Okay. So, if this is possible, then also process and its we can evaluate the proper initial and data of the reversible, but there are certain that involves internal equilibrium initial state. So, characterized as, and when we are infinite number of element of each systems for which the different initial temperatures, and do this particular analysis about infinite number of isobaric processes used to take from the initial non-final equilibrium state. Now, one such example I can, so whatever we have talked about in the thought process, it goes, for example, we have a bar, a metallic bar between a and low temperature reservoir TL, thermally insulated, heat can be conducted through the. So, obviously, we can, as long as getting conducted, the temperature along the distribution along the bar can be linear fashion, by we can find out of temperature, that is L temperature with respect to means the length of the bar. Of the bar is L. So, assuming a distribution of temperatures, equations Ti minus T0 minus by L into X. From these equations, all the intermediate points on TL, we will talk about the slope of the line, we will talk about the, with this knowledge of the slope, temperature distribution at any location. And ultimately, this is that at one instant we can remove both the, if you try to plot is now kept it, but only difference is that with the reservoirs. It cannot come out, have a final equilibrium that is nothing but T0 plus, this can be drawn as the final. Now, problem we as if we have a gross, but what we can make small volume ellipse bar, and for this we can actually evaluate equilibrium temperatures. And now element we write that is equal to minus SI entropy minus initial, we say only for dV. Once we find element dV, which temperature Ti, Tf, the entropy first, then we can integrate of this from, that means L is equal to x is equal to 0 to x is dash will give you SI system. This is the analysis to do problems where we entropy change, which the goes from non-equilibrium state and that is process. So, after having talking about reversible and irreversible, now principle of increase in the in our previous lecture we discussed for the universe is always reversible processes, processes are irreversible, the change in the entropy is always positive, and which are actually, but we have modeled reversible process can connect with involve external mechanic, internal, external thermal and chemical. We calculate system entropy and all these values, ds is expression we will talk about that the terms ds always positive. Now, with this idea inequality talk about the, so what does this entropy change of the universe for every, thus when an is the entropy of the, and with this is called entropy, which means always increases. To prove it in a more, we can say another way that we can actually prove entropy is by calculating, assuming thermodynamics for which the end always greater than the initial. This is true, this has to be true. So, for that reason ensure that initial state I have on final state F goes in an irreversible, that is the conducted between I. Through this process we can get to initial state and reversible, irreversible and reversible, okay. The reversible isothermal we can show that as, and for that evaluate the which is represented as a case, we say in this manner the process IF, we say irreversible. So, we can write minus SI to initial state which says go K to J. So, let us see the K minus SI, reversible adiabatic equal to SK, so SF is equal to, and for the where from this process A to J we can join point from the, we join, we get the plus that it is actual isothermal process. To J you draw thermal curve process, and finally entropy at I. So, whenever point J is located, that means for the process delta S is equal to S. This conclude the fact that cyclic process transfer that happens and reversible, that is at temperature and all other process any heat transfer because the processes are at. So, considering this, the only heat transfer K and I have written Q as is reversible one process for which 0, which means your work transfer W. Second law puts the restrictions not enter the systems because it is interacting with no secondary reservoir. Heat interact at temperature T dash. So, the systems, so means it cannot be. So, considering this, we R is nothing but T dash is always less than, that means process we can write this expression which says Sk minus is always greater. So, already we proved for reversible and irreversible delta S is greater. So, we proved it particular system. Finally, in terms of entropy that entropy can be, and the entropy change of the second one is can be found, and imagine that the process to change in fact this was in the graphically in their previous that in a first the entropy change of the system multiple number of parts we can calculate this entropy, that is process F to J. So, all for all this we calculate this entropy we can we land up having that is delta S is greater. Now, obviously the entropy of this is always greater than 0 and this equal when delta S is equal to equality 7 does not hold good, we say delta S is of entropy. So, I will summarize with following: increase in the entropy of the system, increase in the disorderness. By disorderness for a particular thermodynamic, the free expansion process of means more freedom reservoir volume, the decimal dissipation of work which is in the reservoir temperature. Disorderness with respect to heat bar is the loss of jet is not any heat engine. For example, important metallic bar thermodynamically as energy, but this will not be utilized to, and this goes as a and more rated system definition for entire universe which involves when it experiences it always moves greater disorder. Entropy of the universe, law of thermodynamics, entropy is to go only at absolute temperature. Temperature is the basic, the thermodynamic parameter 0 and the say it is about minus 273, this is not state, this number does not come, we say that this entropy is that you look at it is a point function. If you recall the first law we do dw plus du is a point function, but d path functions and this point function and path are related. That is the assumption that we make in the beginning. True, because this or in a can be written in terms of PdV and TdS. Here ds V stands for the volume. This point function, relation of the point function is even though it is involving work and heat. So, differentials of work replaced with terms of internal energy. So, this is the another significant entropy. We conclude we will try to solve a have discussed of our right, which we call this as entropy calculations I have explained that the mathematical problem we have a reservoir, we have T naught, high temperature T naught, low temperature reservoir, and there is a bar between low temperature high and there is a thermal this region there is a change from T0 to T is up. Now, reservoirs are disconnected, this entire thermal there is 0. So, delta S bar it assumes. So, what we see is the initially the system is at the final state. So, to going to model this, going to create a small Ex. In fact, this is the length of the bar and what is the volume element, and this small bar area times, and for the mass, because you can multiply rho. So, it is mass. For this small calculate is equal to dm dt delta t. dq can be a d. One is with respect to a. Written that the final initial temperature is T. So we change for the small for this. So this can be written as ds for the small volume ds, but SF small volume element, that can be written as cyclic Q by T from initial to final. dq from this you can write ds volume element dB, it as P A, because dx is constant, we can write I to T dt. So we know initial temperature, we know final. So this equation can, so this can be S element volume element d, integrate it, final form of this rho, that is ln Ti, Tf and Ti can be as minus rho a T0 minus TL by into Tf dB element with respect to dx. This can be for the entire bar, which is the actual expression SF minus S, but of d for the small volume d entire length x. So now we can of integration that minus Si the system equal to rho a integration of ln Tf 0 minus L into Tf into dx. This is, if you recall, ln a plus dx is equal to 1 by a plus bx ln bx by this form be integrated. Si Cp ln by Tf plus I T0 minus divided by T0 minus T into a T0. So here all the C 0 8830 A meter square T 400 Kelvin L 200 Kelvin. Putting them, we can SF minus Si is system 18 A Cp is 12 joule per kg Kelvin, and in fact we say entropy of the is 0 because surrounding is d. So this plus surrounding delta S universe is also greater, that is for a state, also prove here. Problem is again of entropy principle. Problem statement is refrigerator, it is the temperature of the body from that of temperature, which is initial is to be reduced to, and in fact this are T1 and observer temperature. See that to talk about this through a refrigerator, that takes the work input, this work input and it must take from this body the heat rejected to atmosphere W. So now able to apply this entropy principle, that universe greater than or equal to 0, and basically our work, of course, did somewhat what is the minimum work, that is the so for this entropy universe on it delta S S2 minus, because body goes from temperature T2, then that is refrigerator is cycle S and since it is Q plus W, that T1. By clubbing all together, S2 minus S1 plus Q by T1 greater than or equal. We can say into S2 plus Q plus is greater than, which means Q is greater T1 minus S2 minus Q. So, this is the conditions amount of work done for the refrigerator. This is the situation. The question is that minimum T1 into S1 minus Q. This is the minimum work required. Refrigerator entropy principle. I conclude this lecture for your attention.